Hello everyone, my name is Alex Medina Fernandez. I'm a mechanical engineer international undergrad student, and today I will be presenting the first 2 points of the first project of this course, which is Material Science ESC 220. So starting with the first question, which is how do we find Young's module, I'm gonna explain the three main ways of finding it, because those are the ones that for now we're applying. So starting with a little bit of a breakdown of what everything means. This is stress. Stress equals force divided by cross-sectional area. Then strain. Strain equals the difference between the final length and the original length divided by the original length. And then as we can see, the formula for Young's module is nothing else but stress over strain. Now, with this method, which is basically using the graph, what we will do is just pick 2 points within the elastic region. As you can see here, point number two and point number 1, these are the ones that will intersect when you select these 2. So for example, right here, we have, for example, here, we could get 0.01 and 0.015. Those will be our 2 points. And where they intersect with the curve, those will be these two stress points. And that's a way to calculate Young's module. Now, the final formula that I'm going to show, it's nothing but the breakdown of the first formula that I shown. So as we can see here, Young's module, which is an E, equals force times original length divided by cross-sectional area times the difference between final length and original length. So moving on to point number 2, how to find yield point and how to find the yield strength. Well, it is not very complicated, especially in steel. This is steel, by the way. We have a very linear curve right here. It's almost straight. The yield point is nothing but the point where it transitions from the elastic region to the plastic region. So here, as we can see, this is what we call an E, which is precisely that point, the yield point. So this will be our yield point. Now, how do we get our yield strength? Well, we already have our yield point. So now what we will do is an offset of 0.002 of strain. So it will be something very small like this. And then we will do a parallel line with the elastic region, and whatever this other line that we did intersects, that will be our yield strength. In this case, it should be around 155 or 160, as we can see right here. This is the knee, and it won't go any farther than this. So yeah, 155 or 160 megapascals. Thank you for watching. I hope you have a nice day. See you next time.
Hello, my name is Jack Rummel, and for my part of the project, I'm going to be talking about how we can find tensile strength and ductility from a stress strain curve and from various standpoints. So first of all, the tensile strength, also called the ultimate tensile strength or UTS, it's the maximum stress a material can withstand before it starts to neck and eventually fracture. So on the stress strain curve, it's very easy to spot. It's just the highest point of the peak of the curve. And so if we come up here and we look closer to these specific graphs, we are going to figure out that the aluminum graph, that is also a tensile stress versus tensile strain graph, same thing for the steel, which is below. From the graphs, the highest peak is exactly where the tensile strength is. So right here, aluminum would be around 300 plus, because it goes above the 300 line, and for steel, it would be above 250 because it goes above the line. And from our data that we collected, we figured out that the aluminum tensile strength was 312.4 megapascals. The tensile strength for steel was 270 megapascals, and your typical tensile strength for copper is around 210 megapascals. So this value basically just tells us the maximum load the material can carry before it starts to fail. Next, we can use the curve to determine the ductility of the material, these two graphs, which is a measure of how much a material can deform before breaking. And there are two common ways to express ductility, which is percent elongation, which is right here, and then we also have percent reduction of the area, which is right here. So I'll go step by step to try to explain what they are. So percent elongation is just based on how much the material stretches, and you can take the change in the length of the fracture and divide it by the initial gauge length, multiply it by 100 mathematically, which right here is the final minus initial over initial times 100, which is how you get it if you had measuring data points. We're using the graph, so we wanted to find EF, which is the tensile strain right before the material snaps. So if we get a closer look at these graphs, we have two circular blue, which these labels represent E of F. And these are right before where the material snaps. So for aluminum, it snaps right around here. Same thing down here for steel, it's right around here. So from the graphs, we can determine that the E of F of aluminum is around 0.132, steel is 0.429, which we can determine, we can make those into percentages by multiplying them by 100. And then copper, for reference, percent elongation would be around 45%. So yeah, and then we still have to find percent reduced area for whatever material we're finding. And in this case, it's aluminum. So for this one, percent reduction just measures how much the cross-sectional area shrinks due to necking before the material finally breaks. And in this case, we have cross-sectional area initially minus the area final over initial times 100. And based on the data that the lab technician gave us, which is area equals width times the thickness, we're going to get the initial area is 0.5 times 0.0625, which is inches. So the initial area was 0.03125 inches squared, and the final was 0.0156 inches squared. Using the formula we got, we can determine that aluminum's reduced area percentage was around 50%, and your typical reduced area for steel and copper was, steel would be 44%, and copper would be around 56%. Again, this percentage just shows how the material is ductile, and if it has a high percentage, and if it has a low percentage, it means it's more brittle. So in this case, basically to summarize, the tensile strength is the maximum stress at the peak of the curve, and ductility is measured using either percent elongation or the percent reduction in the area in the fracture. And together, these properties can tell us whether the material is strong, brittle, or capable of absorbing a lot of deformation before failure.
My name is Dmitry Germanovich, and I'll be talking about resilience and toughness. Starting off with resilience, in simple terms, it is the elastic energy per unit volume stored up to the yield. The yield is the point right here, right past the elastic region. It's where the material no longer, if let go, will return back to its normal shape or size. So it is the area under the stress strain curve up to yield, as I said, given by the formula resilience is equal to the integral evaluated from 0 to strain of stress, taking an integral with respect to strain. So there's actually a cool thing going on, since the elastic region is basically a straight line, which it's very similar, or it's basically the same thing as the spring. So if you stretch it to a certain point, it will always return back to its normal shape and size. So you could use Hooke's law in this case for stress. So in that case, stress would be given by the elastic modulus multiplied by the strain. So we could then rewrite the formula to get resilience is equal to integral from 0 to stress of the elastic modulus multiplied by the strain, taking the integral with respect to the strain. So if you're solving it, this is the work that you do. Once you work it out, you get the resilience is equal to the stress squared over the elastic modulus multiplied by 2. So when we were doing an experiment, we were collecting data points. So our data chart showed that using the points from the data, for aluminum, we got that the stress is equal to 229.53 MPa, and the elastic modulus was 101,400. This could be easily calculated by taking the rise over run, which is simply the slope of the elastic region right here, and plugging these values into this formula, we get this number right here, where resilience is equal to 0.26. And same thing with steel. We took the data that we got from the experiment. We got that the stress is equal to 152.6 MPa, and the slope, or elastic modulus, is equal to 109,900. Plugging it back into this formula, we got this number right here. I just don't want to bore you with the math. We were also asked to give an example with the third metal. As the previous people talked about it, we chose copper. So I was able to pull up data from copper where the stress is equal to 70 MPa, and the elastic modulus of copper is 110,000. So you can see the values I plugged into this formula right here, 70 squared over 2 times the elastic modulus, and we were able to get this number right here. So resilience, it's a pretty simple topic. There's nothing to it. It's very easy to solve, but toughness is a different story. Toughness is the elastic energy per unit volume until the material breaks, where you can see on the curve, it's the fracture point. So the formal definition of toughness is the toughness is equal to the integral evaluated from 0 to the strain of stress and strain with respect to strain. So doing this, I don't know if it's possible to compute it like this, but there's a way to do it, which is compute by trapezoid, because the curve right here, it's non-linear, so plugging into integral would be very difficult because we do not have the formula for the line. So by the way we're able to do this is by computing the trapezoid, which you do by taking the average of the stress between each pair of points, you multiply them by the strain, and then sum across the whole test. So the math for this thing, it's pretty lengthy, so I didn't want to bore you guys and write it all out, so I just plugged in the values myself into this formula, and I was able to get this right here, where toughness for aluminum is 32.9, and toughness for steel is 102.2. So if you're going to compare the two values, you can see aluminum, what we got is 0.26, 32.9. Steel, much smaller number than aluminum. Steel, much larger number than aluminum. It just goes to show that aluminum has a higher resilience, but limited toughness, and it's the opposite way around for steel. And that's the end of my part on resilience and toughness.
Alright, so based on the movie from Spider-Man Homecoming, we can figure out the ship's weight by knowing that F is equal to the weight, which is equal to mg, and we determined that a typical boat, the ship, would be around 5 times 10 to the 7th newtons. And we know that stress is equal to force over the area, so we also concluded that Spider-Man used say around 10 strings. Each strand would carry around 5 times 10 to the 6 newtons. And area of a spider silk, like a typical spider silk, like with a diameter of 1 millimeter, would vary around 7.85 times 10 to the negative 7th meters. So if we plug in A, this number here, and F, which is also this number here, to find the strain, we got to find the stress. Stress would equal 6.25 times 10 to the 12 pascals, and typical stress would be around 1 to 2 gigapascals, which is nowhere near this number. So if we go even further and try to solve for the strain or the elongation, we know that strain is equal to stress over Young's modulus. If we plug in the stress number over Young's modulus, 6.25 times 10 to the 12th over 1 times 10 to the 10th. We're gonna get 625, which is the distance, which is like saying a typical web stretches, like 1 times itself. This stretches 625 times the amount of a regular web, which is basically impossible, which just goes to prove that it is a fictional movie, and Spider-Man holding the ship in half, even though it's cut, is impossible.